Hello, students, and welcome to the 16th lecture on particle physics. In the 15th lecture, we have discussed about the parity violation in beta decay, observed for the first time by Wu and her collaborators on the suggestion of Li and Yang and many others. Now, today, I'm going to introduce a topic which is important to understand that what was the driving force. Because of that, electrons prefer to come out in a particular direction. Remember, while I was discussing about cobalt nucleus, I told you that this is cobalt nucleus with J equal to 5. This is the nickel with J equal to 4. And we had electron and anti-neutrino in this same direction to conserve total angular momentum. Okay, and then we reverse the direction of the magnetic field. Now every guy was in the opposite direction, and we found that the electrons in this case, if they prefer to come out in the southern hemisphere direction, in the latter case when we reverse the direction of magnetic field, and because of that the direction of angular momentum got changed, the electron now, instead of coming out in the southern hemisphere, they are coming out in the direction of northern hemisphere, and that means there is an asymmetry. Now, what was the driving force which was making electrons to have a particular direction? And that is nothing but the helicity of the neutrino or the helicity of the anti-neutrino. What is helicity? Helicity is the projection of a spin in the direction of the momentum of the particle. This is the projection of a spin in the direction of the momentum of the particle. This is a unit vector. Therefore, I can write simply it as P upon mod P, or I can write it as sigma dot P upon mod of P. Now, this can have a plus 1 value, or it can have a minus 1 value. Plus 1 value would say that the spin and the momentum, they are aligned in the same direction, and we call such states as right-handed helicity states. And here, when spin and momentum are in the opposite direction, we have the left-handed helicity state. Now, a massless particle will have a definite helicity. For example, if I talk about neutrinos, then neutrinos will have definite helicity. And this is because, just take a layman's example. I'm talking about two fellows. They are running on a road. Two fellows, they are running on the road. One is, say, has got a speed of 12 kilometers per hour, north to south direction, and another fellow has a speed of 15 kilometers per hour. Then all the time, this fellow will be ahead than the first fellow. But if we ask that fellow that where is the other fellow, he will say that, he will look back and he will say that he's coming along my direction, he's coming to us, and that means he is going from north to south direction. Similarly, instead of that, if I take, for example, a scooter and a bike, say one is 60 kilometers per hour and another is 80 kilometers per hour, and if I ask the same question from this guy, then he will have the same answer, that he is coming from north direction and this is going to south. The other fellow is also going along the south direction. But if the first fellow has, these two fellows have started from the same point as in the previous two cases also, but the first fellow has got a speed of 15 kilometers per hour or 20 kilometers per hour, and another is a racing car which has got a speed of 300 kilometers per hour, then what will happen? That after some time, when this fellow will look back, then this guy, he will say that the other fellow is going in the backward direction. Therefore, they had started from the same point. They were going in the same direction. Initially, when we asked the question from this fellow, first fellow, then he said that the other is also coming in the same direction. But since there is great change, relative change in the velocity, and because of that, when he will turn back, he will say that the other fellow is going in the backward direction. That means it has both the right-handed as well as the left-handed helicities. Similarly, this is true for particles. If I talk about a neutrino and a photon, then, or I choose two frame of references, one in which photon is sitting and another in which neutrino is sitting. Since neutrinos are also massless particle, therefore, if the neutrino is moving along this direction and we have a frame in which light is sitting and it's moving also in the same direction, since both of them are almost, this is traveling with a speed of light, this is also massless particle traveling with a speed of light, therefore all the time they are going towards the south direction and there will be no change. If instead of that, if I talk about an electron and a heavy particle here, a muon is 200 times more massive, then since its speed is speed of light, while electron is also not very massive, 0.5 MeV, therefore it is something like the cases which I have dealt with in these cases. Therefore, in principle, an electron which is moving towards south will have more chances to move in the southern direction for the fellow which is sitting in this frame, which is light. But if we talk about a muon, then muon is a heavy particle. Its speed will be smaller than the speed of light, and therefore after some distance, from this frame it will look like the muon is moving in the backward direction. Therefore, for a massive particle, always it can have a left-handed helicity and a right-handed helicity. But for a massless particle, always it will be in one direction. And in the case of neutrinos, it is found that all neutrinos are left-handed. That means the momenta and spin are in opposite direction, and all anti-neutrinos are right-handed. Momenta and spin are in the same direction. In fact, we shall talk about how helicity of the neutrinos were determined, and it was found that neutrinos are left-handed and anti-neutrinos are right-handed. Therefore, it was found that neutrinos are left-handed and anti-neutrinos are right-handed. And then we are going to take a simple example of pion decay. Pion decays to muon and anti-neutrino. Though the phase space consideration tells us that it should decay into E minus plus nu E bar, because this mass is very small in comparison to the mass of muon, but still almost all the time a pi minus decays to mu minus plus nu mu bar instead of decaying into particles of light masses. Okay, therefore the important point is that this decay is very rare while this has been observed. Who is responsible for that? What physics is responsible for that? And the answer to that is it is because of the helicity of the neutrinos. Since we are talking here, for example, this I have taken pi minus. Similarly, you can take pi plus, where you will have mu plus plus nu mu. Therefore, pi plus all the time decays to mu plus and nu mu, rather decaying into E plus plus nu E from phase space consideration. Phase space, the available momentum states in the final state that we are talking about. Here, if the particle is less massive, then you have more momentum states available. Therefore, chances of decay should be more for the pion, but in general, it does not happen. Or similarly, we can talk about the other decays later in this course, where we will find that really for the massless particles, the helicity are different, but for massive particle, the helicity can be both left-handed and right-handed, while when we compare electron versus muon as the choices, then for muon it is much easier to go into the left-handed and right-handed helicity states because of its mass, rather than an electron going into left-handed and right-handed helicity states. Therefore, what I am talking about, a pi minus that is decaying into mu minus plus nu mu bar, or a pi plus that is decaying into mu plus plus nu mu. Now, since the helicity of the antineutrino is fixed, always right-handed, therefore momentum of the emitted nu mu bar will be along the direction of the spin angular momentum. That means, say, I am talking about a pi minus, its spin is 0. Now, it is decaying at rest, then that means the momentum of the neutrino will be exactly opposite to the momentum of the muon, because we have to conserve linear momenta. We have seen that p mu plus p nu mu bar, this must be equal to 0 to conserve linear momentum, as this is equal to p pi. Therefore, say muon is going in this direction and antineutrino is going in this direction. J is 0 and we cannot violate total angular momentum conservation law. Now you see that what I am telling you, that all the time antineutrinos are right-handed. That means the spin is along the direction of the momentum of the particle. Now, to have J is equal to 0, what we will have to get is that the spin of the muon also in the direction of the momentum of the muon, and that means muon is also right-handed. Similarly, the other thing that I was talking about, electron, why not electron and antineutrino? This is because if you remember, we keep nu e and electron in one doublet and nu mu and muon in another doublet. Therefore, particles of the same nature, same type, same kind, they were kept in first generation, then in the second generation, and so on. And now all neutrinos are left-handed. Therefore, it was expected that the electron and muon should also be left-handed. But here what is happening? That the emission of antineutrino, which is always right-handed in nature, forcing muon to become right-handed or forcing electron to become right-handed. Now, the nature has two choices. Either it can decay to electron or it can decay to muon. It cannot decay to a tauon because tauon's mass is much larger than the pion mass. That will be violation of energy. Therefore, what we are talking about, there are two choices. Either a pion will decay into a muon or it will decay into electron. Now, given a choice, since electron is 200 times much smaller in mass than the muon. Therefore, for the electron to become right-handed, for the nature is more difficult than taking muon to be in the right-handed direction. Therefore, what happens? All the time, a pi minus decays to mu minus and nu mu bar instead of decaying into E minus and nu E bar. Similarly, if I talk about pi plus, then as you can see that nu mu, I am talking about a pi plus, and this is mu plus, and this is nu mu. Or you can take otherwise also. Pi plus, this is nu mu, and this is mu plus. Both are one and the same. Either you take this case or that case. Now what is happening? That all neutrinos are left-handed. Therefore, spins are in this direction. Since pi plus is a angular momentum 0 particle, therefore, this forces us that to conserve angular momentum, mu plus should be right-handed. And given again a choice between E plus and mu plus, for the nature it will be much easier to keep mu plus into a wrong helicity state than to make E plus into a right, left-handed helicity state. That will be wrong helicity state because it is member of with a muon type neutrinos, mu plus. So therefore, the point is that if I am taking this to be j equal to 0, all neutrinos are left-handed, then this mu plus in this way also is a left-handed particle. Therefore, here mu minus is becoming right-handed. Here mu plus is becoming left-handed. And given a choice between electron and muon, it is much easier for nature to make muon to be a right-handed particle. And here it is much easier to make mu plus to be a left-handed particle. Now everything is fine. We are taking these two processes, pi plus and pi minus. As you can see that I am showing the neutrino to be going in the upward direction and mu plus going into be in the downward direction. But equally what I can tell you that you can make this choice also. Mu plus is going in the upward direction and nu mu in the downward direction. And since nu mu is a left-handed particle, therefore your mu plus is a left-handed particle. Now here also you can do the same and you can say that mu minus is right-handed as anti-neutrino is right-handed. Therefore, the important point is that if I am talking about pi minus, for example, here we have nu mu bar, here we have nu mu. Now we take the mirror reflection of this. Now what will happen? As we know that spin has nothing to do with mirror reflection. Therefore, this is a right-handed anti-neutrino and this was mu minus. This was also right-handed. Now, spin does not change under mirror operation or parity operation. Therefore, what will happen when we will see the mirror image? Now, mu minus will go up and nu mu bar will go down. See the mirror reflection of this without changing the spin of the particles. Therefore, the direction of mu minus, spin was in the downward direction. Direction of nu mu bar, spin was in the upward direction. That means here nu mu bar was right-handed, but when we applied parity operation of spatial inversion, then we are seeing that nu mu bar is becoming left-handed anti-neutrinos. Now, had it been the case where anti-neutrinos can be equally left-handed and right-handed particles, then we should have observed this process. But this has never been observed. And therefore, we say that we have a process whose mirror reflection is not an observed process. And therefore, parity gets violated in the weak interaction. Therefore, in a weak interaction process, what we are seeing that we have a particle pi plus. that is decaying into mu plus and nu mu. Nu mu has the left-handed helicity. Therefore, we have mu plus also. Nu mu is left-handed. Therefore, mu plus is also left-handed. We are seeing the spatial or inversion. Therefore, now nu mu will come up. Mu plus will go down without changing the angular momentum. And we are making this nu mu to be right-handed and mu plus also to be right-handed, which a mu plus will prefer. But since in nu mu, which is a massless particle, it has got a definite helicity, never a process mirror image of this process has been observed. And therefore, we say that mirror or process of spatial inversion is not a good quantum number in the case of weak interaction. And we say that parity is not conserved in weak interaction processes. Therefore, the first result was with cobalt. Then even with this example, we can clearly see that parity gets violated in the weak interaction processes. Therefore, this is the real picture that we have this, the top one is an observed process and the bottom one, which is the spatial inversion, where we see that that is not a possible physical process, and therefore we say that parity is not conserved in the weak interaction. Therefore, we have seen in this lecture as well as in the previous lecture that we have two types of parities, intrinsic parity and the orbital parity of a system. And then when we are talking about the parities of the particles, we also saw that because of the helicity of the neutrinos, we have a preferable direction. And that is why electron at that time, since as you can see in the previous case, let me just go back to my previous lecture. We had J is equal to 5 and J is equal to 4, while as you can see, electrons momenta and the antineutrinos momenta are in the opposite direction. But to conserve angular momentum, their spins are in the same direction. Therefore, here you can see that antineutrinos are right-handed and here electrons are right-handed. But what I had told you that when we are talking about angular momentum J is equal to 5 giving rise to J is equal to 4 and a spin of the electron in this direction and a spin of the neutrino in this direction, the electrons prefer to come in the southern hemisphere. Southern hemisphere means that momentum of these electrons are opposite to the direction of the spin of the electrons. And that is happening because neutrinos have got definite helicity. They will always be left-handed particles and antineutrinos will always be right-handed particle. Therefore, antineutrinos, if they are forcing the electrons to come in a one particular direction. Now, in the second case, which is this case, when I am reversing the direction of the magnetic field such that J is equal to 5 here in the initial state, this is J is equal to 4 to conserve angular momenta, these are in the downward direction. Then again you see that if this is my, for example, this is my electron. Now this time what is happening? That this is my antineutrino. That antineutrino will have right-handed helicity. Therefore, momentum will be in this direction. Therefore, this time all the electrons will come out in the northern hemisphere direction. Therefore, the important point is that electrons prefer a particular direction. And this is because antineutrinos are always right-handed. Therefore, they never allow electrons to come out in equal numbers in both the directions. And that is why asymmetry has been observed. And this is the first case for the Woos experiment. And then we have seen it from the pion decay, and then we come to another very important and interesting topic that I will introduce in the next lecture, and that will be the charge conjugation operation, as this is also a discrete symmetry. This is an internal symmetry, and we say that what a charge conjugation operation does, when it operates on a particle state, we get an anti-particle state. It changes charge, it changes lepton number, it changes baryon number, etc. That we will talk about, without changing its angular momentum, for example, and other properties that we will see. Therefore, stay tuned, and we shall meet in the next lecture to discuss about the charge conjugation operation. Thank you.